Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Very good morning, everyone. Today we are discussing about another violation of classical linear regression assumptions. That is serial correlations or autocorrelations. In the assumptions of classical linear regression model, it is assumed that there is no correlations between residual, this period, with the previous period. Okay. Now, if there is any correlations between this error term or residual, what happen about to the estimated parameters? Okay. Okay, actually, the nomenclature for this one is serial correlation and autocorrelations. Autocorrelation, usually use constitutional data and serial correlations Okay, we are dealing about what is the nature of autocorrelations, what are the theoretical and practical consequences if our model has autocorrelations. The third one about the assumptions. We assume in our classical regression model that there is no correlation between this residual for each period. If there is correlations, what is the consequences? Okay, and how to detect and how to solve the problem if we have autocorrelations. Okay, this is assumptions about no correlations between residuals, this period with another period. Here, the expected value of residual, this period with previous period is 0. If 0 means there is no correlations between the residual for this period and the previous period one. Okay, equation 3 to 5, no autocorrelation or no serial correlations. Meanwhile, this is 12.1. There is a correlations. This means because expected value of mu I, mu j is not equal to 0, for I is not equal to j. This means there is correlations between residual, this period, and the previous period. Why does serial correlation occur? There are several reasons. For example, here, inertia. Inertia, we know that every year, every time, okay, there is a business cycle in our data. Sometime, for example, prices indexes increase and the next period decrease and increase again. So the correlations the data for this period and previous period, of course, correlated. So this is a normal in our data, okay? Because the data is not constant over time. So there is possibility that the data are correlated from time to time. And another one is excluded variables. Excluded variable, this means if theoretically stated that the variable is very important in our model, but because maybe there is no available data availability, so we excluded the variable from our model. So the excluded variable can cause serial correlations. Okay, this is because of specification bias in our model. For example, here, equation 12.1.2. This is Y is a quantity demanded for beef. X2 is price of beef. X3 is consumer income. X4 is price of pork, maybe price of chicken, and price for fish. However, for some reasons, we run our regression with the equation 12.1.3. Okay, we have X2 still here, X3 still, but X4 missing from our model. Okay. Okay. For example, if the true model is 12.1.2, but we estimate equation 12.1.3, that means we excluded the one of important variable in our model. So the excluded variable can create serial correlation. Okay, here we can see for the pattern of the correlations. Here for the figure A, panel A, in the figure 12.1, we have this panel B. We have C here, and then we have D. Okay, we have another one here, E. Okay, here we can see that if our residual has a certain pattern, for example, is in 1, okay, is increase and then decrease again, increase again, and here also is a positive relationship. Okay, here we have also some pattern here, and D also has the same pattern here. This means A, B, C, D indicates possibility there is a serial correlations. However, for the panel E, because the residual, these residuals do not have special pattern, so there is no possibility of serial correlation in the model. Okay, and another factor that causes serial correlation is an incorrect functional form. For example, here our data have a non-linear model, but we estimate our model in terms of linear one. So, okay, some data are far away from the mean value of our data. This is our mean value, AB. Because our data have a non-linear, but we estimate linear one, so there is possibility that our model has serial correlations. Okay. Another problem is about cobweb phenomenon. Okay. For example, in the agriculture sector, okay, in harvesting time, the supply of certain goods abundance So the price decrease. Because the price decrease, the demand for the goods increase. At the same time, because the supply are limited, so the price of the good increase. When the price of good increase, the demand for the good decrease. Then these relationships can cause a certain pattern. For example, we can get constant oscillations or increasing oscillations or decreasing oscillations. So this is a corporate phenomenon. Another one is lag variable. Actually, we have some type of variables. Okay. We have a lag variable here. Lag variable. Okay. We have also lead variable. Okay. We have current here. Okay. This one is a past period. This one is future period. Okay, this is we can use these 3 types of data, but usually we use this one. Usually we use this one. This used okay, here we can also use this one. Sum models. So if we estimate for the future, okay, we can use this one. Okay, this one for the future or next expected data. Okay, actually we have 3 types of variables. Okay, for the lag one, okay, lag one. In a time series regression of consumption expenditure on income, it is not uncommon to find that the consumption expenditure in the current periods depend not only determined by this period, but also from the previous period. Okay. Here, for example, here, this consumptions in equation 12.17. This current consumptions is determined by current income and also previous consumptions. So this beta 3 times consumption T minus 1 can cause serial correlations. Okay, another one is manipulation of data. Manipulation is data. For example, we can create data by interpolating the data or extrapolating data. For example, this is common in economics analysis. Okay. Suppose we have data. Okay. For example, here, yes. We have this one X2. Okay. 2000, yeah. 2001. For example, and then we have here data. We have, for example, here 21, here 27. But in 2002, there is no any data here. Here, for example, we have 35, and then we can interpolate. We can make interpolations for here. For this data is equal to, okay, for the 2002 is equal to 27 plus 35 divided by 2. So we can capture this data by interpolation method. So this means 27 plus 35 is 62 divided by 2 is 31. So we insert the 31 in for the data of 2002. This one interpolations. Also, okay, for example, we have here data or data. For example, we have 39 here. 43. And 7 here. X 5. 2009, here we have 61, 2010. Okay. Okay, until we have here. Okay, 2000. We can continue. Look. 2014. Develop. 2020, for example, we have here 162. Okay. Now we are using the future income, for example, or future data, or lead data. For example, here we have 2021, but there is no data for 2021, 2022, 2023, for example, 2025, 34, 24, etc. Okay, here we can make projections, okay, by using some tools here, okay, and then we use this one. This is extrapolations. This common in econometrics. Okay, here for the data of 2021 to 22, 23 until 24, for examples, extrapolated data. Okay, we can make projections from the previous period. Okay. Okay, this is another the kind of interpolations and extrapolations. Okay, we have census, for example, population census every 10 years. Okay, but we have to calculate the data population, the data for populations. Okay, we have 2010, 2020. Okay, this is a census, but here no data here. Okay, no data here. Here no data. Okay, there is no data. Because the census only every 10 years. So for data 2011 until 2019 are calculated by using the data from 2010. So this one another kind of interpolations. Data transformations. Okay, we can make transformations. For example, we use first difference or another kind of transformations. These transformations can also produce the problem of serial correlations. Okay, non-stationary data. Okay, this one will be intensively analyzed in the next semester for the time series data, time series class. Okay, non-stationarity. Okay, usually economics and financial data are non-stationary. Okay, this non-stationarity data can cause serial correlations. Okay, if we estimate our model, but at the same time we have autocorrelation of serial correlations. So what happened about the estimated parameters? Okay, here this one mu t is equal to rho time mu t minus 1 plus epsilon t. Here rho has a coefficient from -1 until 1. If we have -1, that means we have negative serial correlations. If the rho is 1, it's a positive serial correlations. So in our assumptions, the rho is 0. If the rho is 0, that means mu t is equal to epsilon t. If mu t is equal to epsilon t, that means there is no serial correlation exists in our model. Okay. Okay, in the presence of serial correlations, so our model are still unbiased, still linear, okay, but the estimated parameters have bigger variance. If the parameters have a bigger variance, that means standard error of the parameters also very high. If we have very high standard error of the parameters, this means we have problem about the testing for statistical significance of our model. Okay, if the parameters have high variance, so standard error of the parameters are also high. So, okay, the coefficient will be statistically insignificant. It's the problem. Let's, in other words, okay, our parameters are not efficient. Okay, are not efficient because This is the problem of serial correlations. Okay. In the presence of the serial correlations, our parameters become not significant, even though the variable is very important in our model. Okay. Okay, this is consequences of serial correlation in our model. Okay, this one, for example, here. Okay, this one, actually, theoretically, it is stated, for example, in our model. This variable is statistically significant because the variable is very important. For example, in demand model, income is very important in our model. Okay. However, because there is a very high serial correlations, so the income is not statistically significant. This is the problem of serial correlations. Okay. This is the sample for model. Detecting autocorrelations. How to detect the autocorrelation? We have formal and informal methods. Informal method by using the graphical method. Okay, for example, here we can make the graph. If our graph has certain patterns, for example, like this means there is a possibility that the data causes serial correlations. Okay. Run test, I have to skip this for the run test. We go to Durbin-Mason test. Okay, before we talking about Durbin-Mason, I want to make the hypothesis here. We have null hypothesis here, no serial correlations. Yes. Okay, if H null is rejected, then here we have two types of serial correlation. Okay, we have positive serial correlation. We have negative serial correlation. Here. Okay, for positive serial correlation, rho, yeah, rho is equal to +1. For negative serial correlations, 1. Okay, this one we have two types of serial correlations, positive and negative serial correlations. Okay, we use this Durbin-Mason test. The formula for Durbin-Mason test is like equation 1265. And now, okay, we have assumptions about this Durbin-Mason. version. Before we use the Durbin versions, we have to know this one. Okay. The assumptions for Durbin versions, the first one is the regressions model must have interceptor. Okay. If there is no interceptor, that means you cannot use the Durbin versions. And the second one, explanatory variable are non-stochastic. This means, okay, if you are using, okay, system equations such as simultaneous equation model or other models of system equation model, so Durbin versions no longer valid. The third one, okay, this residual is generated by using first order autocorrelations. First order autocorrelations. If you use higher order autocorrelations, that means Durbin versions statistics cannot be applied for this model. Okay, and the fourth one, the error term from the previous model is normally distributed. The fifth one, the model does not include the lag variable of dependent variable. For example, here, equation 12.6.6 here, this is y is a dependent variable. At the same time, we use here, okay, here we have y t minus 1. That means we cannot use Durbin version to detect whether there is a serial correlation or not in the model, because we have lag variables as independent variables. Okay, and the last one, if your data has have a missing observations, so we cannot use Durbin version statistic. Okay, this means we have 6 assumptions to use Durbin version statistic. Okay, if we use Durbin versions, okay, we have 2 zones here, 2 zones inconclusive. Okay, for example here, this between lower limit and upper limit here, and also 4 minus upper limit and 4 minus lower limit, there is no decision also here. Okay, but if we have here between 0 and lower limit, that means reject is null, or between 4 minus lower limit and 4, we reject is null for negative autocorrelations. Okay, this means if we have our Durbin version around 2, that means there is no any serial correlation problem in our model. So this is the formula. Okay, this is a relationship between Durbin version and rho. Okay, Durbin version and rho. Durbin version is equal to 2 times 1 minus rho. Okay, right here. Okay, Durbin version is equal to 2 times 1 minus rho. Okay, if rho is equal to 0, that means Durbin version is equal to 2. Here, no serial correlations exist. Okay, if rho is 0, that means Durbin Mason is 2. No serial correlation exists. If rho is equal to 1, so Durbin Mason become 0. Okay, let's mean here. Here there is positive. If rho is equal to -1, it means D is equal to 4. If rho is 4, this means there is a negative correlation. Okay, so the ideal one is D is equal to 2, because at the same time rho is equal to 0. That means there is no serial correlation exists. Okay. Okay, this is a relationship between rho and Durbin Masons. Okay, how to detect by using Durbin Masons? The first one, you run the OLS and get the residuals, and then make leg of the residuals, and then calculate the D. Okay, and use the Durbin-Watson table. You can get the Durbin-Watson table in the appendix of this book. Okay. Okay. Here, if you have D is between 0 and lower limit, this means no positive autocorrelations. Okay. No hypothesis is reject no positive autocorrelations. If you have D between upper limit and lower limit, no decisions. It's the same as 4 minus lower limit, upper limit, and 4 minus lower limit. Okay, this table 12.6 is a rule to make decisions. Okay. Okay, here I explained already for this one. Okay. Okay. If we have legs dependent variable as independent variable, so we use Durbin H to know whether there is a serial correlation or not. Okay, Durbin H statistic. This is a Bruce-Pagan test. Yeah, we have a Durbin-Watson test. Now we have a Bruce-Pagan-Godfrey test. Bruce-Godfrey test. Okay, to avoid some of the pitfall of Durbin-Watsons, the statistic, a test of autocorrelations. Bruce and Godfrey have developed a test of autocorrelation that is generally in the sense that it allows for non-stochastic regressors, for example. Okay? And the second, higher order autocorrelations, autoregressive, can be AR1, AR2, and the highest one. Okay. Without going into the mathematical details, which can be obtained from the Bruce-Godfrey test. Okay, this test is also known as LM test. Okay, the procedures as follows. Okay, okay, this is our model. Okay, the step is like this. First, estimate the model and get residuals. Okay, regress the residual with the independent variables from the previous model. Okay, and then Yeah, obtain R square from here. This is from the equation 12.6 here. We have this residual. Okay, we have X and leg of the residual. Okay, here we have T minus P. Okay, if the sample size is large enough, so Bruce Godfrey statistic, this has a chi-square distributions. So we get here n minus p, p from here, the leg of residual here. R square, we get R square from these equations. If this statistic is bigger than this critical value, then we reject null hypothesis of no serial correlation exists. Okay. Okay, how to solve the problem of serial correlations. Okay, try to find out if the autocorrelation is pure autocorrelation and not because of the misspecification model. Okay, if you have misspecification model, that means you have to run again with the correct model. Okay, and okay, we can use generalized least square method to solve the problem of serial correlations. Okay, here how to use the method of generalized least square. Okay, first we run our model, then get the row from the estimated result here, 1291. Okay, we have row here, run the residual with its legs, but without intercept them. Okay, we get row here, and then transform the data into leg here, 1293, and then multiply row with the equation 1293. We get 1294. Okay, and then subtract equation 1291 with 1294. We get equation 1295. Okay, after transforming the data with the row, we get these equations here, 1296, and use OLS to run 1296. So you get here generalized least square model. Okay. Okay, we also can use this one, heteroscedasticity and autocorrelation consistent. Okay, this is a very long method to make some correction in our data. If we have heteroscedasticity and autocorrelations at the same time. Okay. Okay, we can use also us and guts. This topic will be next semester available for the time series model. Okay. Okay. Any questions? No, any question? No problem.
Sorry.
Huh?
I have a question about the interpolation and extrapolation. Can you do that only with time series data, like long series of data? Or
Can you repeat your question? Because your sound is not
yeah,
clear enough.
I mean the about interpolation and extrapolation of data. So is it possible to do that, like to do interpolation with only long time series of data?
Or no, if you only usually in an interpolation data only for example, if we have only one missing data, we can interpolate. Okay, but you cannot interpolate for long time series data. Okay, unless we make for example, we make some projections. Projection, that means we calculate this data by using time series model, and then we calculate for the lead data. Okay, but in your thesis, please mention that you make some projections. Okay. Any other questions? Okay, we use this data. Sorry. Okay, again, we use FUs here. Okay, we are going to estimate, for example. Can you use these FUs in your monitor?
Yes, sir.
Okay. Here we have 115 observations from 1990 first quarter until to 2018 third quarter. Okay, for example, we are estimating for the export, and we have US GDP here.
The last one.
Okay, US GDP, and we have exchange rate. Yeah. Okay, we estimate here. And here we have a linear regression model. Okay. Now we have this one. Okay. Theoretically, if US GDP increase, then our export also increase. This exchange rate should be positive also, because if the exchange rate depreciate, that means our local goods become more cheaper in terms of international prices, so the demand for our local goods also increase. But here we have a negative one. This means it is not statistically significant, but this coefficient is statistically significant. Okay, now we can, for example, we test for the serial correlations. Yeah, serial correlation. Okay, if for example we have a leg one here. Okay, we have a confirmation that null hypothesis is rejected. Here null hypothesis is no serial correlations exist. Okay, for example we have a higher autocorrelations test. Also we have this one. Okay, and then we make residual here. Okay, this one residual. For example, we make its name is error term. ET. Okay, and then okay, we generate sample here. Okay, now we estimate this one. Okay, we estimate. Sorry, we have ET here now. ET same. Okay, we estimate this ET with this leg here. Generate series. Okay, 81 is equal to ET minus 1. Okay, we have ET and ET minus 1. We estimate this one. Okay, but we thought the constant term. Okay, now we have here positive serial correlations. Okay, you can see here the row coefficient is 1, row almost 1 here, and it's significant also. This means we have the confirmations that our model has positive serial correlations. Okay, instead of using Durbin-Wesson, it is better to use this one because we have a conclusion here. No need to check the upper limit and lower limit. So this one is very easy to use this one. Okay, this is Durbin-Wesson also. Okay, you run your residual with its leg 1. So you get a row here. Yeah, row is a 0.9 something, and the row is also significant. That means we reject null hypothesis of serial correlations. Okay. Okay. Now, for example, we transform our data into log 1 because we have a problem of serial correlations in our model. And now we check, okay, here. Now we get the better estimated results because now USGDP is positive as stated by theory. That means this parameter is theoretically significant and statistically significant. Okay, here we have exchange rate. Log of exchange rate is also statistically and theoretically significant. This means by transforming our data into log term, we get the best results of our model. Okay, now we test for the serial correlation in our model. Okay. Okay, here, even though we have a serial correlations, no need to make any corrections because we have the best result here is statistically and theoretically significant. Okay, you have any questions? No question? Okay, here if you use to hex here, hex is heteroscedasticity autocorrelation consistent. Okay, we almost the same. Okay, here I want to freeze here. This one is a hex model, and we estimate the normal one with hex ordinary. Okay, we have here. Okay, if we check here, the coefficient almost the same. Here exactly the same, I think. Exactly the same. We have 2.96 here. Here also 2.96, 5280, same, minus 18 also. Okay. The hack model is also has the same as original one. Okay. Any other questions?